Hello everyone, and welcome to the EWMA, or Exponentially Weighted Moving Average, Code-Along lecture. In this lecture, we're going to review a simple moving average using rolling method from pandas, and then we'll show you how to use the exponentially weighted moving average capabilities with pandas. Let's open up a new Jupyter notebook and get started. As a quick note, for this particular lecture, we're still going to be using that same airline passengers CSV file that can be found in the data folder. I went ahead and moved the file to the same location as my current notebook. Before we actually use it, we're going to need to import a few things. We'll say import pandas as PD, import numpy as NP, we'll import matplotlib.pyplot as PLT, and then since I want to see the visualizations, in my notebook we'll say matplotlib inline. Alright, so once that's actually imported, what we're going to do is read in our data. I'll just create a variable called airline to hold the data frame in. And it's a CSV file, so we'll say airline passengers.csv. You can use tab to autocomplete. And we'll set the index column to be month. Now, typically what we would do is we would say something like parse dates equals true, but that's actually not going to work for us because there is a couple of missing data points inside this data set. So what we need to end up doing is once we see our airline, if we check out the head of it, we see that we have this month index and thousands of passengers, but if we check out the index itself, it's actually not a datetime index, it just happens to be like a string index. In order to fix that, what we're going to do is say airline index. Well, first we'll say airline drop NA, and we'll have that in place to be true. So we got rid of all the airline missing values here. And then we're going to say airline index is equal to PD to date time, and then pass in the index again. We'll say airline index. Now let's check out the head of our data frame. And we see that it includes now the first day of the month, kind of indicating that it's now a date time index. And if we want to check again, we can just say airline.index, and here we see the datetime index. Alright, so we've actually already shown how to create a simple moving average. So just as a quick review, we can create a simple moving average just by creating a new column in our data frame. For example, let's say 6-month simple moving average, and I will set that equal to the airline, and it's called thousands of passengers. Just tab autocomplete that. And we call rolling off this column, and you give it a window. We'll give it a 6-month window. That's in relation to our actual period. So notice our periods are a month each. So it goes from the first month, second month, third month. Obviously, if you had daily data, you'd have to change that. But this is a 6-month simple moving average, and then we're just going to call the mean off of this. So call mean, and we can just copy and paste this. And let's create a 12-month moving average, so a yearly. And we actually saw this in the slides. So then I'm going to take my airline data frame, and I'm going to plot it out. And this is how you can get the thousands of passengers, 6-month simple moving average, 12-month moving average. To get a little more clarity, you can also specify the fig size. So we can specify something like, I don't know, 10 by 8. And you'll get something that looks like this. I'm also zoomed in, so it looks a little blurry on my screen. If you end up zooming out to a normal zoom, it'll look a little better. Okay, so that was the simple moving average, just using the simple rolling. Now what we're going to do is show you the exponentially weighted moving average. And remember that the exponentially weighted moving average overcomes a lot of the weaknesses of a simple moving average. Things like smaller windows leading to more noise. You always have this lag. If you notice at the beginning of this plot, there's kind of a lag there. We're going to be able to fix that with EWMA. It also never really reaches the full peak or valley of the data due to averaging. So you can see here, no matter what our window size is, we're never really going to actually reach the top peak here. And what we want to do with exponentially weighted moving averages is let these more recent points have more weight than these past points. So let's go ahead and try that out. The way you do this is you simply, if we zoom back in here, call airline, and then we create a new column. We'll just say EWMA, and we'll say -12 here. And then we'll say the airline. We'll grab that thousands of passengers column again. And then instead of calling rolling, you call EWM. You can do Shift Tab here, and it says provides exponential weighted functions. And you'll notice that there's a couple of arguments here. There's COM, span, and half-life. And you can see here it stands for the decay terms. So you can either specify decay in terms of COM, span, or half-life, or there's even an alpha term. And we're going to discuss what all that means in just a second. But let's show the span first. Whoops, span, not Spain. And then set that equal to 12. And let's grab the mean here. Run that. And then what we're going to do is say airline, and we're going to plot the original thousands of passengers. And then we'll also plot EWMA-12. And let's see what this looks like. So if we look at this plot, let's actually create the fig size just a little better so we can really get a good look at it. We'll say 10 by 8. If we look at this plot, we can see that the behavior at the beginning is different than the behavior at the end. You'll notice that this sort of seasonality trend is a lot more clear towards the end points than versus the beginning points. And that's because we've weighted the points closer to the present time heavier than the points during the more historical values or the older values. So let's now take a little bit of time to describe the mathematics or the formula behind this sort of exponentially weighted moving average, and then how you can decide what kind of parameters you want to use when you call .EWM. In order to do that, we're going to hop over to the notebook that's provided for you. There's actually some mathematical equations in there that'll be useful to reference. So let's go to that notebook now. And then I'm also going to toggle the toolbar. So let's scroll down. Here's all the code that we just went through as far as the simple moving averages. So we can see we created the 6-month simple moving average, the 12-month simple moving average, etc. And then we kind of saw it here. And it's a little blurry because I'm zoomed in. But now let's go ahead and move on to the exponentially weighted moving average. How does it actually work mathematically? And what are the important parameters that we need to know as users of pandas? So as we just discussed in the previous slides lecture, EWMA, it takes into account and tries to improve on some weaknesses of SMA, or simple moving average. Some of those weaknesses, just to review them, are things like smaller windows leading to more noise. You always have this lag by the size of the window. It never really reaches the full peak or valleys of the data due to averaging, and it doesn't really inform you about possible future behavior. It just describes general trends in your data. So in order to fix those things, we use EWMA. So EWMA, exponentially weighted moving averages, will allow us to reduce the lag effect from simple moving averages, and it will put more weight on values that occurred more recently. So really what we want to figure out is, how do I define that particular weight, that W variable? So there's full details on the mathematics behind this in this link. So if you're really interested in this, you can just click on this link and kind of dive into the mathematics of it. We're going to kind of give you a higher level overview of the math. We'll talk about the alpha parameter a little bit, and then we'll talk about the 3 parameters that you can use when working with pandas. So the general formula for exponentially weighted moving averages is this following formula right here. You have the y value at time t, you have x of t being the input value, you have w of I is the applied weight, and note how the applied weight, w of I, changes as you go from I equals 0, that very first value, to I equals t. And then, as I mentioned, y of t is the output. So really the question is here, how do we define this weight term, w of I? So how am I taking in these input values and getting the output values of that exponentially weighted moving average? How do I decide that weight term as it changes when you start from the beginning of the series all the way to the end? So that really depends on what the adjust parameter you provide .EWM method is. So there's a parameter we haven't seen yet called adjust. So when adjust is true, and that's the default value that pandas provide, the weighted averages are calculated using these weights. So you have y of t, the actual output value, is equal to x of t plus 1 minus alpha times x of t minus 1, plus 1 of minus alpha squared times x of t minus 2, plus etc., so on and so on, until you get this final formula where you have 1 minus alpha to the power of t for that original input value, x naught. And you divide that whole thing by the sum of all the weights. So you can see here, this is essentially an expanded formula of what we have up here, where we're just replacing w of I with this 1 minus alpha at time t. And that's important because we can see that there's a decreasing weight as you move further and further into the time series, because we'll have 1 minus alpha, and alpha needs to be between 0 and 1. And what that will happen, or what that will cause, is that this is a decimal number or a fraction, and then if you keep squaring a fraction or taking a fraction to the power of some other higher number, then what happens is you get a smaller and smaller value. So you can see we're providing smaller and smaller weights for the data as it gets older and older. So that very first data point has the smallest weight attached to it, and the very most recent data point has the most weight attached to it, essentially just 1. Okay, and then we divide that by the value or sum of all the weights. So that's the formula when adjust is true. When adjust equals false is specified, moving averages are calculated as the following. You have y naught is equal to x naught, meaning that first input value is equal to the first output value, and then the rest of the outputs, y at times t, is equal to 1 minus alpha times y at t minus 1 plus alpha multiplied by x of t, that input value. So which is equivalent to using these weights right here. W of I is equal to alpha times 1 minus alpha at power of I if I is less than t, and if I happens to be equal to t, you have 1 minus alpha to the power of I. So basically that's what's going on here. It's just another way of rewriting W of I. Okay, so again, one must have alpha be between 0 and 1. And while since version of Pandas 0.18, it's been possible to pass in alpha directly, it's often easier to think about either the span, the center of mass, or COM, or the half-life of the exponentially weighted moment. So this whole thing that we've been discussing kind of comes down to these three terms that we're about to discuss. So how do I actually choose this weight term? Well, with Pandas, the easiest way to think about it is when you set alpha equal to one of these three possible methods. You either think of it as the span, think of it as the center of mass, or think of it as the half-life. So what do these three terms actually correspond to in a general higher level sense? So span, that is S, corresponds to what's commonly called an n-day exponentially weighted moving average. So in our case, we were dealing with month values, but typically you'll be dealing with daily values. So if you want to use an exponentially weighted moving average, what you can do is use the span argument and set that in your mind as an n-day exponentially weighted moving average, where you just define span by that kind of period that you're thinking of, maybe a 7-day or a 14-day n-day exponentially weighted moving average. So that's how you can think of span. Center of mass, that is the C value that you provide, has a more physical interpretation, and it can be thought in terms of C is equal to S minus 1 divided by 2. So it's kind of a inverse relationship with span itself. Then there's half-life, and half-life is the period of time for the exponential weight to reduce to 1/2. And then you can also do alpha directly, which just specifies the smoothing out factor directly. Typically, when we're working with exponentially weighted moving averages, the easiest one to think about is span. And if you want more explanation on the mathematics behind this, again, check out that link. But typically, we'll just be working with this span parameter because it's the easiest one to just intuitively understand. I would say the one that's second easiest to understand is the half-life, especially if you've dealt with things that have this sort of half-life mathematics before. So what we end up doing, like we just did, is we set a new column, and in this case we said EWM is the span of 12, meaning kind of a yearly span in our case because 12 months is 1 year, and then we take the average and we get this exponentially weighted moving average, and you can see here each year is kind of more and more strongly weighted as you get closer and closer to the end of the time series. And you can kind of play around with these and explore them yourself. Alright, so that's really all there is for now as far as exponentially weighted moving averages. If you're interested in this further than what we've discussed here, definitely check out the link in the notebook that gives you the full details on the mathematics behind this and how it works with pandas. Okay, thanks everyone, and I'll see you at the next lecture.